Video is going to cover another operation that we can do with matrices, and it's enough more complicated that we need its own video here, and that's called the determinant of a matrix. And the thing is it slightly changes depending on the size of the matrix, how you do it. I will first say that it needs to be a square matrix. So 2 by 2, a 3 by 3, and so on. You cannot take the determinant of a 2 by 3 or whatever other, if they're mixed numbers there. Now if you have a 2 by 2, that's pretty straightforward. The determinant of A, which we might write this way. Sometimes we also write it as absolute value of A. Sometimes we write it as the matrix notation, except instead of putting the little bars at the end, we leave it blank like an absolute value there. And whenever you're going to do this, you're going to cross multiply and subtract. So it's going to be 1 times 4 minus 2 times 3, or 4 minus 6 is negative 2. So 2 by 2's not so bad. That's how we do it here. For a 3 by 3, it is going to start getting much more involved. And there's going to be two ways that I'm going to show you to find this out. The second way is probably a little bit easier, but the first way is more general. So the idea is you look at the first row, you look at the first number, you write that number down, then you pretend that the first row and column are gone, and you're going to be left with a 2 by 2 determinant with just those numbers. Then you're going to go ahead and look at the next number in the first row, and you're going to write that down. And then you're going to erase that row and that column, and it's a little hard to see now, but the remaining numbers would be 4, 6, 7, 9. And then we repeat this a third time here. We look at the third number there, and then we look at the remainders after I erase those. We'd have, what, 4, 5, 7, 8. Only extra little trick here is that you start out with plus, and then the second one is going to be a minus sign there. So it goes plus, minus, plus of these. So quick overview here. We started with a 3 by 3 matrix, and we break it down to 3 2 by 2 determinants. And it's going to turn out that if you had had a 4 by 4, you would break that down into 4 3 by 3 determinants. And then each one of those you would break down to 3 2 by 2 determinants. So what that would mean is you have to do 12 separate 2 by 2 determinants. And if you had a 5 by 5, it'd be 5 4 by 4s, 4 3 by 3s, 2 and a partition and a pear tree. Right? It gets really, really messy and involved here. Thankfully, we don't really need to do very big determinants by hand. We can use computers for it if we need to. However, we haven't finished this problem yet, so I would do 1 and then 5 times 9 minus 6 times 8 minus 2 times 4 times 9 minus 6 times 7 plus 3, 4 times 8 minus 7 times 5. And that's going to be, what, 45 minus 48 is negative 3, minus 2 times negative 6, and then plus 3 times 32, negative 3, and we're going to get negative 3 plus 12 minus 9, so the answer to this one is 0. Now there is actually an importance to that being 0, and I will mention that shortly, but I wanted to show you the second way to find a determinant first. I do need to point out that this second way, it only ever works on 3 by 3 determinants. It will not work on 4 by 4 or 17 by 17 or anything else. It only works on 3 by 3, but 3 by 3 are the most common we have to actually do by hand, and so that's going to be good enough for us. And so the way it's going to work is you start by writing down the determinant that you have here. And then you are going to copy down the first two columns a second time. And then you're going to draw 3 diagonals going down and right, and 3 more going up and right. And all of these green ones, you are going to multiply, so 1 times 5 times 9, and 2 times 6 times 7, and 3 times 4 times 8. And all of these are going to be pluses. And then all the red ones, 3 times 5 times 7, they're all going to be minuses. 1 times 6 times 8, and 2 times 4 times 9. And then we just kind of work things out here. 45, let's see, it's 42, 84, 96, 105 minus 48, and 72. And I'm going to go ahead and say that since we know the answer is 0, I'm not going to work that out, but you would have to just work that out there and see what you get. Now, we got our answer here, and I said that the fact that it was 0 actually meant something. And it turns out, here's this fact here. I want to make sure that we talk about this. And the thing is A has an inverse, which we saw in the other video, if and only if determinant of A is not 0. So basically, if you ever take the determinant and you get 0 as the answer, that means that your matrix does not have an inverse. It's impossible. And that's actually going to have a meaning when we are solving equations. We haven't talked about that yet, but I'm just pointing out that determinant 0 is in fact actually a bad thing for a matrix. So obviously we want it to be non-zero if possible. Regardless, that right there is determinant of 3 by 3. Now I already told you that if we have a 4 by 4 like in this next example here, that you'd break it up into 4 3 by 3s, 3 2 by 2s, blah, blah. It's a real pain here. But it turns out this is a special type of matrix that makes our life a lot easier. This is what's called a triangular matrix. And in particular, this is an upper triangular matrix. And what do we mean by that? It means that if you take your diagonal here and you draw your triangle, then the only numbers you have are in one part of this triangle, and everything below that is 0. That's why this is an upper triangular matrix. If all the numbers had been on the bottom and all zeros were on the top, it would be a lower triangular matrix. And so, why do we care about this? Well, because of the following reason, is that the determinant of a triangular matrix equals product of diagonal. So what that means is instead of having to break up this whole determinant into all these different pieces, we can just multiply across these main diagonal elements, and it turns out that's going to be the right answer. Now again, this shortcut only works if you have a triangular matrix. However, if I ever ask you to do something like an 8 by 8 matrix, it's going to be triangular because it'd be insanely long otherwise. But this is a really, really useful trick when it works.